For our first workshop today, we have Alisa from the NIL Foundation presenting about the Placeholder proof system.
Thank you. Hi, everyone. Today I want to introduce the Placeholder. I'm Alisa Cherniaeva. I'm head of research team at NIL Foundation. Firstly, I wanted to describe in details what we would discuss for today. Firstly, I want to give you full understanding. A little closer to the mic. What? Closer to the microphone. Okay. It's better? Yeah. Okay. Firstly, we will discuss why we exactly need modularity and proof system, why we need either for all application we build it on the top all NIL infrastructure. After this, I give you some examples of different setup of proof system, and last thing would be about how we build circuits via zk-LVM and why it's better when just human created it. So, firstly, I wanted to give you some understanding what exactly is Placeholder. Placeholder is a modular type of zero-knowledge proof system based on Planck-style arithmetization with custom gates. And yes, I know what you know all words, almost all words from here, but we have one word here. It's a modular. So I just wanted to give you some understanding why it's important word. So let's start from some, proof life cycle. What happens? Firstly, we have some source of code, and we want to translate into circuit representation. And it's our first phase, it's circuit generation. And we can express any calculation inside code via circuits, which is familiar for proof system. Second phase, it's a proof preprocessor. And the proof preprocessor, we just switch to another parameters of proof system. And circuit generation, it's actually part of proof preprocessor, but for some clarity, I divided into two phases. And just mind it, it's a one-step setup. And the next phase, it's arithmetization procedure. What I mean about it, I mean, all this lookup argument, permutation argument, gate generation, all this thing, I call it arithmetization procedure. After this, we have a commitment phase. It's final phase when we finally get a proof structure. And after this, we verify it. For NIL infrastructure, we use EVM verification. So look, first two phases, it's some one step. And after this, arithmetization, commitment, verification, it can be changed. It depends on what you choose on the first two phases. For now, many other proof systems have a constant design. So we have some constant parameter inside circuit generation and proof preprocessor. Yes, you can just modify it, but it takes a long time. So what I offer in the Placeholder, you just choose your desired properties and get a result in minus. So what exactly is modularity? Which components we have inside Placeholder? So let's start. It's a trust assumption, fields, lookup technique, gate generation technique, general recursion support, EVM verifier, and public input processing. I give you some details about, firstly, trust assumption. When I say trust assumption, I mean what we want to choose, no trusted setup or some minimal trusted setup. So it would be choice between different commitment scheme. And in the Placeholder, we offer two options. First one, it's a list polynomial commitment. You know it, maybe it's a fry inside. So it's not so cheap verification, yes, but it allows us to get some trade-off between proof generation time and verification cost in Ethereum side. And it gets us no trusted setup. The second option, it's a budget version of KZG. It's always cheap verification, but we would have some universal trusted setup. So the second option, it's a field, and yes, it's based on your previous choice. So if you choose LPC plus fry, it would be you can choose any field, but we need to have a property what one of factors would be a big power of 2. For example, it would be pulse field. I give you some factorization, and you see here big power of 2. And if you choose KZG, you need to use field of parent-friendly curves, obviously. Next one, it's lookup techniques. Basically, all lookup techniques, it's divided on 2 approaches. First one, it's depend from main assignment table, and second one doesn't depend from main assignment table size. You can hear about first approach, it's a lookup, Halo 2 lookup argument, plonkup, and we use generalization of plonkup. What I mean about the generalization, I just wanted to put all lookup constraints into one lookup argument. Also, I want to achieve some flexibility inside lookup tables. So if we have some big result circuits and small lookup tables, I wanted to push several lookup tables inside to one physical column. And another option, if we have some small result circuit, I wanted to divide big lookup table into several columns. So lookup constraints would be like this value should contain in first column or second column or third column. It doesn't have any overhead for prover phase, so it's just a plonkup generalization. And the second approach, it doesn't depend on main assignment table. You can hear about like in calc, lookup, baloo, lasso. Yeah, it sounds like it's a better option, but it has some small drawback because we need to use parent-friendly curves for all these approaches. And we suggest to use lasso. Now it's a work in progress to include in the placeholder. But yes, I think it would be lasso. Next one, it's a gate generation techniques. We have 2 options, and first one is our usual Plonkish custom gates. It's a turbo plonk with all constraints looks like this, and we can express any polynomial equation via custom gates. And the second approach, it's IVC Plonkish. You maybe hear about Nova, Supernova, something like that, but I suggest to use Protostar. It has some relaxant Plonkish constraints inside with IVC approach. So if you try to choose what really better for your case, you need to think. If you have some big repeatable computations, it's better to use IVC approach. I will show you some examples of this when it would be better to use IVC, and when it would be better to use just usual Plonkish custom gates. So, and it's a small parameters, but we have general recursion support. What I mean about general? Usually we have some only recursion for independent circuits. So we doesn't have any variables inside one circuit and another circuit, and it doesn't connect it with each other. So what we offer different option. It's a dependable circuits and independable circuits. How I said, for dependable circuits, for example, we have 2 circuits, and output from one circuit would be input for the second circuit. And usually this option is used for when you have really big circuit. And the second one, as we care about our EVM verification, about the verification cost, we have 2 small options for public input, hash input and direct input. Hash input is a good option when we have some public ledger where we can store all public input. It's an option for when we have really big input and we cannot send it directly. It would be not so cheap. Okay, I say something about different setup params for placeholder, and now I want to give you some application, a real application, what have already done on the top all new infrastructure. First of all, it's a ZK bridge, it's mean state verification. So what we have inside, Mina? We have inside pickles verification. What is exactly? It has kimchi verification. Which components would be used inside? It would be circuit-friendly hash function. It would be elliptic curve arithmetics. And that's all. But look, elliptic curve arithmetic, we have two curves in the Mina state verification. It would be Pallas and Vesta, and we need to split all circuits on two parts. All scalar calculations would be executed on Pallas side, and all elliptic curve arithmetics would be on the Vesta side. So we need to have two fields. It would be pasta curve fields. It wouldn't be any repeatable calculations inside, so we need to use custom Plonkish gates. And how I said, Pallas and Vesta, it's best choice for LPC and Fry, so we would be use this option, and we get no trusted setup. As we have some big input, we would have hash input verification, and how I said, we have elliptic curve arithmetic, native elliptic curve arithmetic. Also, we have circuit-friendly hash function. Exactly, it's a Poseidon component, so we don't need any lookups inside. And how it's pretty small circuits. For Vesta, it would be 2 in power 23, and for Pallas, it would be 2 in power 22. Yes, and so we don't need any recursion at all. Second example. It's also ZK bridge. It's for Solana state verification. What we have inside Solana? We have some chain of blocks, and we need to prove it. So it would be some non-circuit-friendly hash function. Exactly, it's a SHA. Also, we would have some signatures of validators. It's YDDSA signatures. So what's the bad thing here? Yeah, the curve isn't suitable for LPC, isn't suitable for KZG because of its properties. So we need to use non-native arithmetics. So how I write here, it would be non-native YD field, and how it's a ZK bridge, we don't want any trusted setup, it would be Pallas native field. And here, why we use just custom gates? We have non-native arithmetics. We have maybe 1,000 validators, so it isn't enough repetition for IVC approach. Here it would be better to use just usual Plonkish gates. Also, it would be big input, so we use hash input verification. It would be SHA hash function, so we need lookup techniques. And how I said, we use Pallas field. It's not parent-friendly curve, so we need lookup technique, which doesn't depend on parent-friendly curves. So it's a generalization of lookup, how I said. Also, it would be pretty big circuit because we have non-native arithmetics. So we need to split it into several signatures, and we can afford to ourselves independent recursion support. Next one. It's an example of ZK Oracle. It's LIDA. LIDA offers us to, transfer data from consensus layer to application layer. And what we have inside? We have inside several Merkle trees, but it's really big Merkle trees. So we have, it's about 10 millions of hash function, and it's not circuit-friendly hash function, so it's pretty big circuit. And here, it's better to use IVC Plonkish style, because we have some small blocks and 10 million repetition. Yes, it wouldn't be so for each hash function. It would be some sub-tree of sub-Merkle tree, but it's better option to use IVC approach. It's a strict requirement from LIDA. It's no trusted setup. So we would be use Pallas fields. We need to hash input verification. It would be again SHA function, so we need lookup technique, what doesn't depend on parent-friendly curves. And we have IVC clone cache, so it's obvious we don't need any recursion because we have already recursion inside IVC approach. And the last example, it's an example of ZK gaming. In our case, it's a speedrun of Doom. What we have inside? Inside, it includes some usual game dev logic. So we need to prove what state transition from some tick states was okay. So each tick state would be contains all objects on the game scene, and we need to prove what it's in the range of all possible states. So what would we have inside? We need to again custom clone cache because it would be different calculations. All calculations is just integer numbers, but we have many Boolean components inside. It requires to use lookup techniques. It requires us to go to the sparse representation. So it would be bigger than just usual integer. So we need to use some native field which is bigger 128 bits. No trusted setup. And here we need to direct input verification because we don't have any public ledger. And look, how I said, it's a pretty big calculation. So we need to just split it into several circuits. And we need to have dependent recursion support because output of one circuit in ZK Doom would be input for another circuit. Yeah. So I just show you several examples of our real use application, and it's for now it's mean what you need to use different modification or different proof system, but here you can just tick on your desired parameters and get a result. And last part. How I said in the last part, I wanted to show you how we can build circuits. And firstly, I wanted to answer to one question: would it better to make by hand or via zk-LVM? Yeah, it's definitely, if just circuit designers try to create circuits, it would be better assignment table. But it takes much time because it maybe takes months. For example, for mina-state verification, it really takes months. And here I don't say about some, low-level circuits like scalar multiplication or just native multiplication. I say about high-level circuits like evaluate component, all layers component, kimchi component, pickles component, all this thing. It's 100 circuits. It's really 100 circuits. I do it myself. It was madness, really. And if we just take zk-LVM, it would be just a minute. And I think it's a great thing. Yeah. But we have one drawback. Yeah, we have drawbacks when we use zk-LVM. It would be more sparse assignment table. But maybe we can avoid it. Maybe we can do it via zk-LVM, like just human design it. So let me remind how it looks like assignment table. Here you see the pictures. Especially it's an assignment table for message schedule in a SHA circuit. But it's just an example. So it's just a real table which has columns, row, all cells in the table which connected with some gates. Gates it's some set of polynomial equations. And we care about total amount of gates and gate degree. Also we care about lookup option is on or off. So Let's think about more monostate verification. I say some words about it. And I split low-level circuits from high-level circuits. And for low-level circuits, for monostate verification would be Poseidon hash, would be PO component, variable-based multiplication. Variable-based multiplication, it's a scalar multiplication on elliptic curves. It would be just native multiplication, addition, subtraction, and last one, it would be inverse. And all kimchi verification we can express from which 7 components. It's even not kimchi. I'm talking about all pickles verification, actually. So, what we would be have inside? Let's think what Poseidon, PO, and variable-based multiplication we create specially for Mina. So it would be, for example, 15 columns, but it's just example. For multiplication, addition, subtraction, it obviously would be 3 columns. And for inverse, we need additional variable, so it would be 4 columns. I haven't time to build all, Mina verification for now, so it would be small example. Just take it for 1 Poseidon, 1 PO, 1 variable-based multiplication for 3 more smaller circuits and 2 inverse component. What we have here? If it would be some simple approach from compiler, what we do? So here we have Poseidon component, PO component, variable-based component. It's always have 15 columns. Like we designed it especially for monostate verification. And here, look, multiplication. We have, it would be like in this approach, just multiplication, multiplication, and multiplication. After this, we would be use addition, subtraction, and inverse. It's just like automatically naive compiler try to build the result circuit. But you can see the problem in the circuits. Yes, we have many empty spaces, and it's just a small circuit. Just imagine if we repeat it in, I don't know, 1,000 times, what we would be have? We would be have bigger columns. It means what we would be have bigger polynomials. We have bigger polynomial operation inside gate arguments in the prover phase, and it really increase prover time. It's bad thing. And yes, it's obvious how we can, what we can do it. Compressed approach. The beginning is the same. It's obvious. We created especially from Mina. Yes, we try to locate it into one row, all multiplication. Also addition and subtraction. And look at this. We have on the second row, when we have addition, we have 12 columns and 3 columns, and it's not enough for inverse. So it would be the next row. So compressed approach would be looks like that. It doesn't have so much empty spaces. Yes, it's a normal thing if we have it inside our circuits, because here it's the best circuit for SHA, and it has empty spaces too. But yeah, what we have, all these small components automatically would be generate additional gates. If we have additional gates, it means what we have additional selector column, because each gate have their own new column. So it would be pretty big total amount of additional columns. And it means what it's not better option. It means what it has some drawbacks, but in another side. Okay, and we have a solution for this problem. It's It's a flexible circuit technique. What we have inside? Inside we have some metric function. It firstly takes all code, source of code, and try to evaluate all params. And let me show you with one params for each components. What would be better execution for this? After this, columns compilers would be connect metric function with low-level components, and low-level components would be adapt inside and assign all gates and assignments in the table in accordance with how many unit columns, rows. Maybe we can restrict some gate degree. Usually it would be 9, so it's have to be some small total degree. It restricts the, it's decrease the total amount of gates, and would be think it would be better to use lookup option or not use, and what we can do with lookup table flexibility. How I said, it can have one column or several columns. Just like this. And let me show you about this example, how it would be look like. This circus was designed specially for Mina. So the beginning is the same. Here, what we would be have. If I try to express all flexible circuit technique in the simple words, it would be remove all intermediate variables and push it into one gate. So try to remove intermediate variables. For multiplication, we have 3, and it's obvious for simplicity, just imagine it would be sequential calculation. So what we would be have for first multiplication? We would be have 2 input variables, but for the next multiplication, we don't need to have it. We just need to 1 variable. So it would be like 2 for first multiplication and 1 for second and the third. After multiplication, we have addition and subtraction. It would be like this. And the inversion. Inversion has some input and additional intermediate variables. We cannot remove it. And we need to have some output variable. So if we try to calculate it, we would be have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, and 15. It would be like variable-based multiplication. Yeah, it's a good example. I designed it specially. But in the general case, flexible circuit technique will give us like this, because it would be exactly how human would be designed with circuit. So what I want to say, in our placeholder we have modularity, and with modularity it's not only about choice of commitment scheme, it also great flexibility inside circuits, so it would be automatically generate result circuits in minutes. Thank you everyone. Maybe you have some questions. I would like to answer for them.
Your ZK10 example, did you compile Doom directly, or did you write custom circuits and recode the game as a circuit?
We translated into circuits, but we use the ZK10 and some, low-level.
You can try with
You can hear me, yes.
Okay.
But, sorry. So what we have in the DOM? Yes, we have some code, and we translated via ZK10 into circuits. So it would be just a few low-level circuits. Like, we need to Boolean arithmetics, we need to some shift arithmetics, we need to pull components, and some native operations. And that's all.
I discussed with Misha, I think, on the Short Knowledge podcast era, and he told me that you can prove I discussed with Misha on the Zero Knowledge podcast Telegram, and he told me that you can prove most of LLVM IR. So in that case, you actually just need to recompile to placeholder, right?
Yeah, yeah.
So you don't need circuits.
It's not actually circuits. How I try to divide it, it's we have low-level circuits and high-level circuits. We need the low-level circuits, but it's generally just constraints and just technique how we express any code inside proof system. So I think that's all. Thank you.